can you solve this geometry challenge? Here's the question. Let's begin with an equilateral triangle. Now let's extend its base such that this segment right over here measures 2 units. Now from here, let's have another equilateral triangle like this. And the question is, what is the area of this shaded region? Now pause this video right now and see if you can answer this question, because I will show you the answer and the solutions in 3, 2, 1. Alright, the answer or the area of this quadrilateral, this blue quadrilateral, simply equal to square root of 3 square units. And that is the answer to this question. And of course, the question is, how do we get this result? In this video, I will show you 3 different approaches to answer this kind of question. The first one is by using Ptolemy's theorem. The second one is by using rotating figures. And the third one is my favorite, using invariance principle. Now let's begin with our first method, which is the Ptolemy's theorem. Now in order to use the Ptolemy's theorem, we need to make sure that this quadrilateral is inside our circle, or a cyclic quadrilateral. And Ptolemy's theorem states that the product of these two diagonal is equivalent to the sum of the product of its two opposite sides. And now, how do we know that a quadrilateral is a cyclic quadrilateral? And that's very simple. If the sum of two opposite angles simply equal to 180 degrees. Now on our figure, we know these two triangles are equilateral triangle. In short, those interior angles must be equal to 60 degrees. Now, this is 60 degrees, is also 60 degrees. And also, we know that a straight line equals 180 degrees. Since this is 60 degrees, this angle right over here must be equal to 120 degrees. Now, 60 degrees plus 120 degrees, this is exactly 180 degrees. In short, this blue quadrilateral can be inscribed in a circle, or simply this is a cyclic quadrilateral. Now, since this quadrilateral is inside the circle, and we want to use the Ptolemy's theorem, let's connect now these 2 points like this. And now, let's use the concept of what we call the inscribed angle theorem. Since this is 60 degrees, all of these arcs must be equal to 120 degrees. In short, this angle right over here must be equal to 60 degrees, and this angle right over here must be equal to 60 degrees also. Because this arc measures 120 divided by 2, this is 60. Again, 120 divided by 2 is 60 degrees. We are now ready to use what we call the Ptolemy's theorem. So let's begin. First, let x be the side of this small equilateral triangle. Now, since it is an equilateral, the bottom part is also equal to x. Now, the whole thing, the whole segment right over here, the whole base is equal to 2 units. Therefore, this segment from this point to this point must be equal to 2 minus x units. Also, let y be the side length of this big equilateral triangle. Now, this diagonal right over here, let's call this as k. Now, we can now apply what we call the Ptolemy's theorem. And if we do that, we have k times y equals y times 2 minus x plus x times y. And if we simplify this, the right-hand side becomes 2 times y minus x times y plus xy. Now, negative x times y and positive x times y is 0. So this becomes k times y equals 2 times y. And we know the value of y is not equal to 0. So we can divide both sides by y. In short, the value of k must be equal to 2 units. So we can replace this k with 2 units like this. And now at this point, we are now ready to find the area of this quadrilateral. So what we're going to do is to break this quadrilateral into 2 triangles like this. Because we will use this concept to find the area of this triangle. So the area of the triangle is simply equal to 1/2 times AB times sine of the included angle. Now we have this included angle 60 degrees, and we have the side length 2, 2 minus x, and x. In short, the area of this blue triangle must be equal to 1/2 times 2 times x times sine of 60 degrees, while this green triangle must be equal to 1/2 times 2 minus x times sine of 60 degrees. Now, we can simplify those areas a little bit because 1/2 times 2, this is just 1. So the area of this blue triangle simply equal to x times sine of 60 degrees. And this green triangle, we can simplify this further as 2 times sine of 60 degrees minus x times sine of 60 degrees. In short, the area of this quadrilateral simply equal to the sum of these two areas. So 2 times sine 60 degrees minus x times 60 degrees plus x times 60 degrees. And this 2 is simply equal to 0. In short, the area of this quadrilateral simply equal to 2 times 60 degrees. And the value of 60 degrees simply equal to square root of 3 over 2. These two cancel out. In short, the area of this quadrilateral simply equal to square root of 3 square units. And that is our answer to this question. So using the Ptolemy's theorem, we get that the area of this shaded region or this quadrilateral simply equal to square root of 3 square units. Now, how about the second solution using rotating figures? So let's do that. First, we know that this angle is 60 degrees for sure. This is an equilateral triangle. And also, this quadrilateral is a cyclic quadrilateral. And if we connect these 2 points, these two angles create 60 degrees and another 60 degrees. Now, also take note that if we let the side of this small equilateral triangle be equal to x, this segment right over here must be equal to 2 minus x. And again, this is an equilateral triangle, so this side must be equal to x also. Now, let y be the side of the big equilateral triangle. Now, from here, let's call this angle be equal to alpha and this angle be equal to beta. In short, alpha plus beta simply equal to 60 degrees. Now, using again the concept of inscribed angle theorem, this angle alpha inscribe this arc. In short, this angle right over here must be also equal to alpha. And with the same reasoning, this angle right over here must be equal to beta. Now, we have here a big equilateral triangle, so this angle must be 60 degrees and another 60 degrees. Now from here, let's extend the base like this, such that this measure be equal to the side length of this small equilateral triangle, or simply equal to x. Now, we don't need this circle anymore, so let's get rid of it. And now from here, let's create a triangle like this. Now, we have here alpha, and this is 60 degrees. And we know a straight angle measures 180 degrees. Therefore, this angle right over here must be equal to 60 degrees plus beta, because alpha plus beta adds up to 60 degrees. 60 plus 60 plus 60, we have 180 degrees. Now, also take note, this is y units, this is x units, and an included angle of 60 degrees plus beta. On this triangle, we have here y, we have here x, and an included angle of 60 degrees plus beta also. In short, these two triangles are congruent using SAS postulate. In other words, this angle right over here must be equal to 60 degrees also, and the angle on the top must be equal to alpha. And also, since they are congruent, the area of this figure, this triangle, is the same as the area of this triangle. Now, also notice that the base angle is simply equal to 60 degrees. In short, the angle on the top must be equal to 60 degrees also. In short, we have here an equilateral triangle. Now, what is the side of this equilateral triangle? This is just 2 minus x plus x, or simply equal to 2 units. And we have a formula to find the area of this equilateral triangle. We have s squared times square root of 3 divided by 4. Now, what is s? This is just 2. So, substitute s equal to 2. We have 2 squared times square root of 3 over 4. 2 squared is 4. 4 over 4 cancel out. Therefore, the area of this shaded region must be equal to square root of 3 square units. And that is our answer to this question. So using rotating figures, we get that the area of this quadrilateral simply equal to square root of 3 square units. Now, for the last method, this is my favorite, and this is called the invariance principle. So let's begin. Now, if we search invariance principle in geometry on Google, you will arrive at this page, wherein it says that the invariance principle in geometry is a problem-solving strategy based on identifying properties like distance, area, or cross ratios that remain unchanged or invariant, even when a geometric figure undergoes transformation like translation, rotation, reflection, scaling, or projective distortion. And also take note, it allows you to solve complex problems by replacing a complicated or moving configuration with a simpler, highly symmetrical one. And also, I have a video about using invariance principle. So this is our channel, Zahlen Mathics. Now let's begin solving this problem using the invariance principle. Now what we're going to do is to change our perspective of this figure, and we can make this small equilateral triangle a big one or a small one like this. But if we want to find the area of this blue shaded region, what we're going to do is to make this small equilateral triangle be, or the area of this, be equal to 0, like this. In other words, we now have a single equilateral triangle with a side length of 2. And we know how to find the area of this. This is just s squared times square root of 3 over 4, wherein s simply equal to 2. And if we simplify this, we get the area of this equilateral triangle simply equal to square root of 3 square units. And that is the answer to this question. Therefore, given this figure, we can say that the area of this shaded region must be equal to square root of 3 square units. So using Ptolemy's theorem, rotating figures, and the last, the invariance principle. And as always, we are done.